All right, welcome everybody. Good morning. So I am here to talk about Project Valhalla again. I have talked about Project Valhalla on this stage before. How many people here have seen some of my past Valhalla talks? So great. Okay, so I'm hoping that this will all be received as good news. We've made fantastic progress in the last year or so. I don't know who dubbed Valhalla Java's epic refactor. But it's a great name, and so I've stolen it. It wasn't I didn't make it up, but it really is an epic refactor in that it is a deep cut through the language, the VM, the runtime. So we've been working on it for a while, and so I'll sort of I'll put the summary up front. So we've been working on this nearly 10 years, which is kind of appalling. And during those 10 years, we've built probably 6 distinct prototypes, all of which I would characterize as research prototypes aimed at learning a specific thing. And we've had numerous rounds of refinement. First aimed at doing more, and then aimed at reducing the intrusion into the specification, into the implementation, and especially more recently into the user model. And the progress that we've made in the last year has largely been around simplifying the user model and improving our results for migration compatibility, which are both good signs of being basically there. And we really do feel like we have finally turned the corner and that we're pretty much there. We know what it looks like. There's still obviously some work to do. There are 4 JEPs that are out publicly. The first of which, JEP 401, already has an early access release that you can go download today. And then there are several other JEPs that are queued up behind it, layering more features on to the model as we build towards the bigger vision. Okay, so this will be a review for a lot of people, so I will speak quickly, as I often do. Why are we doing Project Valhalla at all? Well, the main motivation that got us started with this was flatness and density of memory layouts. So object graphs in Java are relatively pointer heavy. You have small islands of data connected by memory and directions between them. So that means that our data is not as flat as we would like it to be. And it's also not as dense as we would like it to be because a lot of memory gets used by pointers and by object headers. And in the 30 years that Java has been around, the hardware motion has been such that the relative cost of memory operations versus CPU operations has diverged dramatically. And so cache misses become relatively more expensive over time, to the point where in 30 years ago, a cache miss and an arithmetic operation were in the same order of magnitude of cost. Now they're several orders of magnitude apart. And so the memory layout we have now is just begging for cache misses, and the memory layout we have now is a consequence of the semantics that we have now. And so, to illustrate this, and I've shown this picture before many times, that, if I have an array of XY point objects, the array is really an array of object references, which is really an array of pointers. Each pointer points to an object that has a header. Headers take memory, and these objects are, even if they're allocated, in close to the same time, so they're near each other, the garbage collector is going to come along and move them all around the heap. And in a lot of cases, the memory layout that we would want for an array of XY points is something more like this. And so the questions that Valhalla has been addressing itself to is, what do we have to do in the platform to make this possible? And we spent the first probably 8 years answering that question. And then the last 2 years, we've had the luxury of focusing on the latter questions, which is, what code can we ask users to write to get a layout like this? And can we do so without turning Java into C++? So there's also a secondary motivation that is, more that has less of a numeric measurement, but is equally important, which is what can we do to reduce the impact of what I call Java's original sin, the rift between objects and primitives? So in 1995, the choice to have primitives that aren't objects was basically a forced move. We needed to have reasonable numeric performance. Java couldn't be taken seriously if a numeric performance was poor, but it's a cost we've been paying for the last 30 years. We all feel a little bit dirty when we use integer instead of int. And everywhere you look in the language, in the VM, in the way we code, there are pervasive cost and frictions due to the difference between primitives and objects. And this keeps getting bigger. So in Java 5, when we did generics, you can generify over all the types except for these 8 primitive types. And in Java 8, when we did lambdas, we saw this explosion of hand-specialized types like instream and int-to-long function. And again, we didn't really feel like we had a choice on those things, but it didn't make us very happy. So, it's worth reminding ourselves that we can do everything we want with classes. We don't really need primitives, except that we like their performance characteristics. And this is the classic bad choice to give to users when you say, well, you could do it this way, and everything is clean and abstract and object-oriented and wonderful, or you could do it this way, which is messy and ugly and faster, and we all know which one people pick. Right? And so when you're in that situation, you want to be able to give people a choice where things are clean and fast so that they pick the clean thing. And that has been the main motivation for Valhalla. The war cry all along has been codes like a class, works like an int. Now, healing this rift is no small task, because if you sort of make the list of things that are different between primitives and objects, it's a long list. Classes are user-defined, primitives are built in. One has members and supertypes, the other doesn't. One has identity, the other doesn't. One is nullable, the other isn't. One is polymorphic, the other isn't. The list just goes on and on. And so trying to unify these concepts under under one model is tricky. And the first time we tried it, we didn't really like the outcome, and so we iterated on that. So, it's worth, pointing out, acknowledging the elephant in the room. We've been doing this for 10 years. What the heck have we been working on? And I remember when we first announced Valhalla, I was at Java 1, I was on a panel, and James, say hi, James, turned to me and said, in full view of the audience, this Valhalla stuff looks really cool, but you do realize you've signed yourself up for 6 PhD theses, don't you? And my heart kind of sank, because I was kind of hoping it was going to be 2, but James was right, and it took us a long time. But the good news is, even huge projects yield when you have enough smart people bashing their heads against it. So, we built multiple prototypes. We built 3 prototypes of generic specialization to try to understand how types and erasure flow through generics. We built several VM prototypes, including the minimal value types prototype, which had all new bytecodes, vload and vstore. And then we iterated on that prototype. The current prototype, or the most recent one, was called L-World, where we were unifying the L and Q class descriptors. And each one of them moved the ball forward. It disclosed some aspect of the problem. A number of them racked up successes in one form or another, especially performance. But until recently, we hadn't really addressed the hardest questions, which were, what is the programming model that makes sense to Java users, that doesn't feel nailed on, that provides migration compatibility for all of these classes in the JDK that are morally already value types, like integer and optional and local date? How do we migrate those compatibly to be value types without leaving a trail of evidence? And one of the hardest questions, and this is not a user-facing question, but an implementation-facing question, is where is the division of responsibility between the language and the VM? Because VM engineering is more expensive than language engineering, so you have a limited budget to say, we need the VM to do this for us. And so what items we should use that budget for, it took us a while to figure out exactly what the right division of responsibility was. So in the spirit of the Gartner hype cycle, I sort of I tried to characterize what a journey like this looks like in a decade-scale engineering project. So, of course, at the beginning, you start out with the absurd optimism of youth, thinking, oh, this is going to be easy, and look how cool it's going to be. And of course, that doesn't last very long. And then eventually, reality hits you, and you think, oh my God, this is impossible. What idiot signed me up for this? And then is the long, slow climb up toward what I call the peak of complexity, where you're chipping away at the problem and you're not really thinking about the elegance of the solution. You're just trying to say, can I meet the requirements? Can I solve the problem? Can I answer all the annoying questions that people ask me at JVMLS about will it do this and will it do that? And it's possible to get there. And the mistake a lot of projects make is shipping that solution when they get there, because you think, well, we're here, we solved all the problems, right? And fortunately, we've had the luxury to not ship that solution and let it, let it ripen, a little bit longer. And we got to the next phase, which I think a lot of projects don't get to, which I call the virtuous collapse, where you find a simplification and that begets another simplification and the snowball rolls and until you get to the point where you say, where did all the complexity go? Totally, not all projects get here. And so I'd like to believe that we've arrived at the last phase, which is the one where everybody says, what took you 10 years? That's so easy. So we'll see if we're there. I hope we're there. So, okay, so what's the view like from the peak of complexity? Well, it's a mixed bag. The view was great, right? The performance, we had amazing performance results. We had, and I've shown some of these, here in the past, so I'm not going to go through them in detail. But things like matrix multiplication, we got 6x throughput improvement, 1000x allocation reduction. Iterating over arrays of objects, like arrays of pairs of integers, 3 times faster with a loop, 12 times faster with a stream, or like this last one is my favorite, which is iterating over that and doing a immutable accumulation, being 8 times faster than the old way, which means that we can write immutable code and get the performance of mutable code, which is awesome. Right. So these were like, really, positive successes from our peak of complexity prototype. So we should ship it, right? Well, the view might have been awesome, but the weather sucked. The programming model that you had to use in order to write this code was it was not what we wanted to wish on Java developers. And what's interesting about it is the organizing principle behind the model. It was one that we came by honestly, where we said, all right, well, we have primitives and classes today. We have int and integer. Let's make a linguistic concept that models the relationship between int and integer. And that felt like it should make sense because everybody understands int and integer. And when people say, well, what does this primitive class thing mean? You could say it's just like int and integer, and they would know how it works. But the problem is int and integer suck. And this perpetuated all of that suckiness into the infinite future. It put a lot of mental bookkeeping on users because there were so many different aspects of how int and integer differ. And so, there was a lot of mental load for users. It was intrusive in the syntax. If you remember this, this version, you would declare a primitive class P, and it would give rise to 2 types, p.val and p.ref, a primitive-like class and a reference-like class. But it was very intrusive in the programming model. Users felt hit over the head by it, and migration compatibility was not good. So, the peak of complexity, well, the peak of anything, is a local maximum. So once you've climbed your way to the peak of complexity and you realize it's not where you want to be, it's going to be a fair amount of work to get somewhere else. So we had an honest approach, modeling primitives and boxes, but it wasn't good enough because, like I said, it was trying to cover too many different things. And under the hood, we had that same complexity where there was a lot of VM surface. There were new bytecodes. There were new type descriptors. All of these things, created challenges for migration compatibility. So we rebooted our effort. So before we go through the details, I sort of want to go through what were the problems that we had to push our way through. If the goal is more flatness and density, well, what are the impediments to flatness and density? And it was a little bit like the Spanish Inquisition sketch, where we started out thinking the main impediment is identity. Identity and nullity. Identity, nullity, and initialization. Identity, nullity, initialization, and it kind of got ridiculous after a while. So I'm going to go through all of these, one by one. But the point is that there was not just one big impediment to do this, and everything, gives you nice flattening. So we knew early on that object identity was flattening enemy number one. So in the Java object model, every object has a unique object identity, and that is surfaced in the programming model through the equals equals operator. That compares two object references and say, do these references both refer to the same object, which is, is the identity of these two objects the same? And identity is useful in an object-oriented system. It enables things that we use every day. It enables mutability because it means that there is a well-defined place where the state lives. It enables non-trivial polymorphism, so that you can have the layout of an abstract class that's embedded into the layout of its subclasses, and a reference to the subclass is really a reference to both. It enables the intrinsic monitor that every object has. So identity is important. We use it every day, but not every class needs identity. And for the classes that don't need identity, identity is often a source of bugs, because equals equals and dot equals don't agree with each other, and people will accidentally use one instead of the other. The consequence, and the reason identity is an impediment to flatness, is that it effectively requires that we use that each object live in one fixed place at a time. Maybe it can move around because the garbage collector moves it, but every object has a well-defined home, and then we use indirections so that multiple places can point to the same object. Unless we get saved by compiler heroics like escape analysis, but otherwise identity means an object has to live in one place, and that is an impediment to flattening, and also to scalarization. So syntax-wise, how do you declare a value class? You stick the word value in front of the class. That's the whole thing. A value class is a class whose instances have no identity. So it's a semantic statement. My instances are just their state. They don't have any extra state that identifies which object this is. Necessarily, this means you're giving up some flexibility. You're giving up the things that identity enables, like mutability, but it also enables optimizations. And there are a lot of classes today that are logically, could be value classes: numerics, dates, most tuples, cursors, things like that. Those are all good candidates for being values. Semantically, value classes are pretty similar to classes. They can have all the things classes can have. They can have fields and methods and constructors and type variables. There are only a few small differences. The fields are final. The class is final. The equals operator compares two instances by their state, by comparing the fields, rather than comparing their identities. There's no lock. So if you have a synchronized method in one of these classes, you'll get a compiler error. If you try to synchronize on one of them at runtime, you'll get a runtime error. Same thing is true with some other identity-sensitive operations, like weak references. You try to take a weak reference to a value object, you'll get an identity error. And there are some small limitations on what classes you can extend. And that's it. That's the semantic differences between value classes and non-value classes. And instances of value classes, which we call value objects, are objects. And the object references are still there in the programming model. We just hope that they're going to be optimized away at runtime, so that there's no physical pointer representing them. Their key runtime characteristic that makes them different from identity objects is they're freely copyable. If I have a value object, it's basically, it's just its state. So it's just a bag of fields, which means the compiler is free to shred it into fields, pass the fields around in registers, and reconstitute it into an object if it needs to, whenever it wants, and that's not an observable operation from the user code. So, the VM is free to scalarize and reconstitute value objects at will. The effect of this is that most on-stack usage, where let's say you allocate and reallocate a value object in a loop, it's not going to allocate anything. It's just going to shred it into its fields, hoist the field into registers, and mutate the registers. And in particular, we get nice optimizations for calling conventions, where if I'm passing a value object, like a point, to another method, it's not going to pass a pointer to a point. It's going to hoist the x and y separately and pass those in registers to the callee. So we get a lot of benefit. We call this stack flattening or scalarization. We get a lot of benefit from that, regardless of what's happening in the heap. And this is what enables immutable accumulators to perform as well as mutable accumulators, because there's not really an object that we have to allocate. We can just hoist its state into registers. So, quick example to visualize this. This is an example of an immutable array cursor. So I've written it as a value record. Records can be value classes too. What does the cursor contain? It contains a pointer to the base of an array, a reference to the base of an array, and an offset into that array. And it has the obvious methods of, is there a next element? Give me the next cursor, which increments the offset and then returns a new cursor, or get me the element of that cursor, right? So trivial. And I can write a loop that looks like I'm allocating a whole pile of cursors as I iterate through an array. But what's really going to happen is the cursor is going to get shredded into its field, base and offset. Base never changes. The only thing that happens when I go through the loop header is I'm incrementing that offset. That's going to turn into a register increment. So all of the cool tricks that we get when escape analysis works, which it doesn't always work. Now we have ironclad, proof that the VM can use to say, oh, I can scalarize the heck out of that thing, and and you can write nice, clean, immutable code, and I will give you fast machine code. So that's pretty cool. So we have a JEP for this, and the plan is a phased delivery. So the first JEP has a limited scope, which is just value classes. So syntactically, the only change in this JEP is the one new modifier on classes and records and what have you. We're going to migrate a few of the JDK classes, integer, optional, local date, as demonstration that these work as value classes. And so the focus in this first JEP is mostly on the semantics and some basic optimizations, mostly calling convention optimizations. We're not going to get full flattening yet. But we will get, some flattening in the heap as well. So, like I said, we'll get full scalarization of value parameters, value returns in calling convention and on-stack operations, and we can get flattening in the heap for small nullable value classes. So basically, if the payload is less than 64 bits, because we need an extra bit for null, we can flatten those on the heap as well. And so this is a good start, and the EA is out now. You can download that today. And we think, this is a gentle introduction for users because there's only one new concept to think about. You can ask yourself, does this class need identity? No? Well, then disavow it. And that's really all the decisions to be made. I'll point out that there's a benefit in disavowing identity, even if you don't care about performance, because identity is an unneeded degree of freedom for a lot of classes and potentially a source of bugs. And if you don't need it, don't use it. So it doesn't take long before you realize that identity is not the only impediment to flattening. Another impediment is nullability. So if I have a nullable reference to a complex, I need to encode all of the values of complex numbers, and I also need to be able to encode null. And the numeric types we have, int, long, double, and if like complex is built on long or double, they use all their bit patterns already. So if I need to represent another bit pattern, it means I need another bit somewhere. So a nullable long needs 65 bits. Well, that's really 128 bits because because longs want to be aligned on most architectures. And so nullability is, at the very least, a flatness hazard. It's also, a density hazard, but it's also a flatness hazard. There is, potential interaction with data races that can inhibit flattening of nullable values that have larger payloads as well, and I'll talk about this more in a little bit. But it's also important to point out that most numeric code doesn't want nulls. There's a reason primitives are not nullable. Well, there's many reasons primitives are not nullable, and this is one of them, is that in most numeric code, nulls just get in the way. And so, like identity, this is a degree of freedom that has a cost and may not have a benefit in some cases. And if it doesn't have a benefit, we should be able to disavow it. And so letting users opt out of nullability for variables is a well-studied problem. A number of languages that are sort of similar-ish to Java have already adopted, adopted some flavor of this: Scala, Kotlin, Swift, C#. And they've all chosen the same syntax, for a good reason, where the bang character indicates non-nullable and the question character indicates nullable. Where these characters come from, well, it's a circuitous path, but they come from regular expressions. So in regular expressions, question mark indicates a cardinality of 0 or 1, bang indicates a cardinality of 1, star 0 or more, and plus 1 or more. And there actually have been languages that have cardinality-based type systems that explored these concepts in great detail. And then the languages that picked up on nullity control said, well, I don't need the sequence stuff. I don't need the 1 or more, 0 or more stuff, but I'll take the exactly 1 or the 0 or 1 stuff. And so this is a well-studied problem. It's not a small problem. It's not a small feature, but it's one that users have consistently asked us for and has benefits both within Valhalla and outside of Valhalla. So in one of the earlier iterations, in the primitive classes iteration, we tried to make value types non-nullable by default on the theory that, well, primitives are non-nullable and that's how we want them. But that turned out to both impose a lot of cognitive load on users who had to keep a mental dictionary of which classes are nullable and which ones aren't, but also it played havoc with migration compatibility. So when you bring non-nullable types into your language, it raises some new questions around initialization, both for fields and arrays. Fields are, for fields, if I have a field of type string bang, well, what's the default value of that field? Well, the VM is going to want to put a null there. But that null is outside the value type of the type I've given the variable. And that's kind of a conundrum. And so the way we addressed this was by strengthening the definite assignment rules that Java has, where we say a null-restricted field has to be given a value by your constructor prior to the superclass call. A superclass constructor call. So there's an interaction here with some other work that's going on, JEP 482, which is flexible constructor bodies. I think Archie is here today. Archie's over here. He's been working on that, which is awesome. Where historically you couldn't put anything before the superclass call, and that's, okay, you can usually work around it, but sometimes it gets pretty inconvenient, and it would be nice to be able to put some statements before that superclass call. And so we restructured how constructors work to have a pre-initialization context where you can do computation that doesn't use this, then you make the superclass constructor call, then the rest of the constructor, you can use this. And we also said, well, we'll allow a limited use of this before the superclass constructor call to initialize the fields. And that turned out to be a really powerful thing, because by engaging definite assignment analysis, we could make sure that that field was never seen to be in an invalid state. Arrays are a little trickier because they don't have constructors, but we can use kind of the same thing. So ordinarily, if I allocated an array of string bang, I'd get an array full of nulls, and so the elements of that array would be seen to not obey the type of their component type. And so what we're going to do there is something that is more akin to Well, let's imagine that arrays have constructors, and the ordinary constructor just takes a size, make me an array of this size. But for some types, you have to use a constructor that says, and here's the default value to fill the elements in with, or here's a lambda, which we can initialize the elements with, and hopefully do this in a way that that it doesn't become a performance impediment, where the VM can optimize away initializations that it knows is going to be just an all zero value. So having type restrictions brings in some initialization challenges, but we think we can solve those. And we can implement this feature with no regard to value types or other Valhalla features at all. And so we have a JEP for just that. It doesn't have a JEP number yet, but it is in the bug database, which is basically adding cardinality markers to the type system and threading it through the type system through inference and bounds conformance. And pattern matching and conversion and all of that. With some dynamic checks where we do widening conversions. So if you assign a nullable thing to a non-nullable thing, you'll get a null check, just like we do with unboxing today. And similarly, dynamic null checks at separate compilation boundaries like method entry. So that if someone passes in a null to a parameter that is expected to be non-null, you will get a null pointer exception early without having to pepper your code with objects required non-null all over the place. Now, like when we announced this, there was a lot of blather on Reddit about this isn't how to do null restriction. Because it's not how every other language necessarily does null restriction. And the reason for that is we had an extra goal that some other languages didn't have, which is it needs to be migration compatible to add nullity markers to your APIs. Because otherwise, we're like giving people a gift they can't open, right? Here's a great language feature, but none of your old code can use it. Sorry, too bad. So it has to be binary and source compatible to add nullity markers to existing APIs, and that perturbs the language design a little bit, but that's sort of what we do. So if we take these previous two JEPs, which is value classes and null-restricted types, you can sort of imagine that there's a child JEP of the two of them that lay the foundation for null-restricted value class types, and that's what unlocks some more of the flattening for value classes. But again, initialization is a challenge here. So when you create an object, under the hood, we allocate some memory, the VM writes some zeros to it, and then we evoke the constructor that writes the real values of the fields to it. And there are long-standing gaps in this process where a not fully initialized object might be exposed to user code, whether it be the superclass constructor or an overridable method of the class. And historically, these have been annoying, bug bait, but not integrity failures. But for some value types, the physical zero is not a valid instance of the class, and exposing that to user code would be an integrity failure. And so again, we need to lean on stronger definite assignment analysis in order to make sure that these uninitialized values are never exposed, to user code. So we spent a lot of time chasing sort of a different solution to this, and before we found the right solution. So we spent a lot of time thinking about, well, does this class have a natural zero? Is that a good default? Yes for integer, yes for complex, no for rational, et cetera. And instead, we decided that it was better to just tighten the holes in initialization so that you never observe something in its default state. And once you do that, doesn't matter what the default is, because the user is going to have to give a good value before anybody can observe it. And so that was, like I said, a synergy with JEP 482, which we didn't start with Valhalla in mind. We started it because we were like fixing an annoying gap in the programming model, and then we realized, hey, that annoying gap is like, we have that problem here in Valhalla too, and that worked out really, really nicely. So one of the things that we did was we pushed, we not only tightened the language's definite assignment analysis, but we also pushed verification of definite assignment into the VM. And by doing it in the verifier, there's no actual runtime cost, which is pretty cool. And so we invented this, and Dan will talk about this at length in the next slot, this concept of a strictly initialized field, which means it's initialized before anybody can see it. There's no new modifiers on field, there's no strict modifier, but what there is the language does DA analysis, and then the verifier backs up that DA analysis to make sure that it really is given a value before it's exposed. And this ensures that value objects are only observed in a single state, which in turn enables more compiler optimizations. It also ensures that null-restricted fields are never observed to be null, even though the VM is going to put a null there as a default value in a string field. So at this point, you might be inclined to say, wait a second, is that everything? Because that didn't seem like very much. And yeah, that is almost everything. And the way we got there was by focusing not on modeling primitives versus classes, but on the semantic differences between them, identity, nullability, et cetera, and exposed each of these as a language feature that where users could opt out of unneeded degrees of freedom. So if you don't need identity, you can opt out of it by being a value class. If you don't need nullability, you can opt out of it by using null-restricted variables. And beefing up existing language features like definite assignment. And when we did this, the sort of linguistic complexity just sort of collapsed. The author opts out of unneeded degrees of freedom, and then the JVM gives us the best performance it can given the semantics you've selected. Now, a bunch of things happened behind the scenes to enable this. There was a sort of as we were simplifying the user model, we were also simplifying the VM model, and these really fed into each other. So once the language had a way to say non-nullable and capture that in the class file, the need for separate L and Q descriptors in the VM went away. Once we were able to prevent partially objects from being observed, the need to have a different initialization model for value classes went away. Therefore, the need for new bytecodes like vnew went away. Therefore, the impediments to migration compatibility went away. And it was like one day you woke up and all the complexity was gone. All right, it wasn't quite like that, but it sounds good. But interestingly, the hidden star of the show turned out to be the strict initialization thing, which is surprising because nobody asked for that. That was not a feature. Anybody was banging on our door saying, Valhalla needs strict initialization. It just turned out that by plugging an existing hole in the initialization protocol, a whole bunch of problems just went away. So I already talked about how small the new language surface is. The new VM surface is limited to a new bit on classes for value, a new bit on fields for strict, a new attribute on fields for don't write nulls to me, and some bootstraps for creating null-restricted arrays, and some new verification rules. That's it. No new bytecodes, no new type descriptors, no new constant pool forms. This is pretty amazing. And kind of as a bonus at the same time, a bunch of things that we had thought were just going to be impossible. All this time we're saying, we're never going to get that. We're just going to have to live with that. Became possible. So like I said, the unified initialization protocol, having default values for value types that weren't the physical zero, which is something people really didn't like, that restriction. And we thought, there's just no way around it. But with better initialization, there's a way around it. Similarly, value classes that have abstract classes as supertypes, even value abstract classes with fields, no problem. It all works now. And these were things that we had just given up on being able to deliver. So it is really quite interesting. So the lesson from all this, which is totally not surprising, is performance comes from clean semantics. Flattening is and should be a pure optimization. You don't want to have the user saying flatten this, flatten that. That's you want to be able to write a program with the desired semantics and have the VM figure out, I can implement that really efficiently. And we all know the history of performance-oriented language features. The register keyword is is the poster child for that. And so all this time we were saying, that feels like too much of a register keyword. And now we don't have any register keywords. Well, we don't yet. I'm not done. But the challenge was finding the right set of semantic levers that both make sense to the user and make sense in the absence of performance characteristics, but also enable the VM to reward the program with better performance. And the primitive classes model, that wasn't it. So by letting people opt out of degrees of freedom we don't need, that pretty much was all we needed. Plus, fixing the initialization initialization thing. The other sort of interesting thing is migration compatibility is kind of like the canary in the coal mine, where there were all of these bad migration modes that we were nailing bags on the side to deal with, and that was or should have been an evidence that our model just wasn't clean enough. And when the model got clean enough, migration compatibility wasn't even a question. It just all worked. But don't get me started on migrating serializable classes. So speaking about serializable classes, it is well known that no significant feature gets out of the room without wrestling with serialization, and this is no exception. Strict initialization, which enabled a whole bunch of things, is at odds with how serialization is implemented, because the way serialization is implemented is allocate an empty object and then poke a bunch of field values into them. And if you want those field values to be strictly initialized, that doesn't work. Now we have a bunch of work going on in serialization, better model for serialization that I've talked about before, that is a great match for serializing value classes. I'm not sure that's going to be ready in time, and we don't want to take on another project-to-project dependency, but there's going to be some serialization work involved in this feature, because of course there is. Okay, so I kind of lied when I said we're done, because there's another elephant in the room, and that's the Java memory model. The memory model is defined purely in terms of reads and writes to heap variables, and the reference to an object and the fields of that object are separate variables. And the object references to value types are still there in the language model. They're still object references, even if they're flattened away where they disappear from physical memory. And that means we have to preserve the illusion that the Java memory model is still talking about a reference to an object, unless, of course, we change the language. And whether or not we can preserve this illusion depends a lot on the hardware. So most modern hardware only gives us efficient 64-bit atomic loads and stores. I'm really hoping Intel is going to give us a Christmas present one of these years. Is anybody from Intel here? Please, Steve, please. 128-bit atomics, please. Because this is a pervasive constraint on how much we can flatten. And it's related to an old sad story, which is the tearing of 64-bit primitives, from the early days. So back in Java 1.0, because few machines had cheap 64-bit atomics, the language spec said that access to a long could be treated as two 32-bit accesses. And in the presence of a data race, it's possible you could see the high 32 bits of one write and the low 32 bits of another write, which we call tearing. And that seems very un-Java-like. Why did we allow that? Why did we allow reading a variable to give us garbage? Well, because we had to. Numerics had to be fast. Otherwise, no one would take Java seriously. Concurrent numeric code was rare. Programs with data races are already broken. We had a lot of excuses we could hide behind, right? It's like, oh, the program's already broken, so it can be a little bit more broken. And technically, it didn't violate type safety, right? Because all 2 to the 64 bit patterns encode valid longs, so it's not a type safety problem, right? You can see the excuses piling up. But the reality is, we didn't have a choice. It was a forced move. And then the hardware came along and saved us because we have efficient 64-bit atomics now, so this doesn't happen in reality. But the old sad story becomes a new sad story, because value objects may very well be larger than 64 bits. And if we want to flatten them, we still have to confront what we call it structure tearing. So if an object has invariance, like a range where the low end has to be less than the high end, and someone wrote up a nice, clean, object-oriented value class for this, where the invariant was enforced in the constructor, and it was observed not to hold at runtime, well, that would really make people's heads explode. Right, and so the default has to be integrity. We can't allow these objects to tear without extra permission from the user. So how do we make the decision about flattening larger values and admitting the hazard of tearing under race? And this is a complex trade-off. It's a trade-off of performance for integrity. And depending on what your program does, you may or may not want to make this trade-off. If you're doing, operations with big matrices of complex numbers and it's all single-threaded, well, of course you want the flattening. And you're willing to take the tearing because you're not accessing the thing, under data race anyway. But other value classes have invariance, and it would be very surprising if they were to tear. So there's no one-size-fits-all answer. We're going to need some help from the user. The default has to be integrity, but there has to be a way to opt out. So our current thinking on this, and this is very half-baked, but our current thinking is to allow a value class to opt into relaxed atomicity by, in this example, it's implementing a marker interface, but it could be a modifier on the class where we say, yeah, I don't have any invariance to protect. Go ahead and flatten me, and if you access me racely, you get what you deserve. Maybe this is the right model. Maybe it's not. It is a little bit of register keyword, so we're not 100% comfortable with it, but it's an idea under consideration. A little bit of good news is all those restrictions about atomicity don't apply if we have something that is basically immutable all the way up. Because if there's only ever going to be one right to the thing, we don't have to worry about races between rights, and we can flatten much bigger objects. So a little bit of a scorecard to see how we're doing flattening-wise. So in all cases, value objects are going to get excellent flattening on stack and in calling convention. So good scalarization, no matter how big they are, until we run out of registers. Nullable value types with payloads of less than 64 bits can be flattened in the heap pretty much all the time. With non-nullable value types, we pick up that extra bit, so we can flatten 64 bits all the time. We can flatten larger values if they're final all the way up. We can flatten larger values if the class author opts out of atomicity. And if we get that Christmas present from Intel, then we can flatten bigger things. And 128 bits is a lot bigger than 64. There's a lot of classes that you can fit in 128 bits. So that's kind of what we're hoping for. So okay, so that's a lot. We have we have an EA of the first JEP. We have other JEPs in various stages of prototypes. The last JEP I didn't talk about much, but it's basically a mopping up of eliminating all the gratuitous differences between int and integer bang. So can you use it as a receiver? Can you override a method that returns integer with one that returns int? Can you use a primitive as a type argument? Are int arrays covariant with integer arrays? All of those things are possible. We just haven't done them in the first round because we can wait for them a little bit. But there's a JEP for these, and it's actually been stable for quite a while. There will still be some minor differences between int and integer bang, such as how they interact with overloading. But for the most part, the goal is to make int and integer bang almost synonymous. Now, even if we had all this stuff today, which we don't, there's always more to do. So I'll just name two of the obvious things that are follow-on work that are probably in your heads right now, and which we could talk about at the workshop later. So it will not take long before people say, okay, great, I can write a half-float class or a complex class or a unsigned int class. Where's my operator overloading? Yes, we know. We understand that numeric code wants to be able to control operators. We also know that operator overloading in most curly brace languages has been an unmitigated disaster. And so we're trying to avoid rehatching that same disaster. The model that we have in mind is something that is loosely based on type classes from Haskell. I'm not going to talk about it much more today, but the idea is rather than overriding individual operators, group the operators that come from a common algebraic structure and put them in an interface together where they can be specified that addition and multiplication participate in distributive law and things like that. So no ad hoc operators, no using the plus operator to overload list addition, list insertion, etc. The other big follow-on project, which we've talked about a little bit at JVMLS in past years, is generic specialization. That's something that we've been working on a slow burn for a long time. Remy's going to talk a little bit about his prototype for it later today. There's actually a quite detailed design draft that's been around for a few years, the parametric VM document that John has written. And so we think we know how to do this, but we've been focused on getting the basics done first. So just to sum up, and I'm only a few minutes over, the last 2 years have seen amazing progress in exposing an actually sane programming model that can unlock the flatness and density optimizations that we had identified in earlier prototypes, and also give us a lot better migration compatibility. The resulting VM and language surface is shockingly small. Still big implementation project, but the intrusion into the surface is shockingly small. We have 4 JEPs on the books, one of which is in EA. The others are in various stages, like I said. And watch this space. So thank you very much.